In our last set of videos, we started looking at single joint control. Within single joint control, we learned about velocity control of a DC motor. We learned that we can control the rotational speed of a DC motor by changing the volts, and that this conversion is made by the motor velocity constant represented by K. The ability to control the velocity of our motors is somewhat useful in robotics. However, in order for us to successfully control our robot, we have to control not only the velocities, but the positions. Today we're going to be looking at how we do position control of the robot joints. We'll be looking at a couple of different approaches to position control. The two main categories into which we will divide the approaches to position control are open loop control and feedback control. Feedback control is then divided into two categories of its own, on-off control and PID. For today, we're going to be focusing on open loop control, and we'll get a brief introduction to feedback control. In future videos, we'll go into the difference between on-off and PID control. To help me explain position control, I'm going to use a little device as a demonstration. This device is called a motorized slide potentiometer, and we'll be using these devices in class. This device consists of a DC motor over here, and if I rotate it up, you can kind of see that the shaft of this DC motor is attached to a gear. The gear has a belt drive attached to it, and that belt drive moves this slider left and right. So if I take a battery, here's my battery, and I apply a voltage across these two terminals, the slide will shoot to the other end. And if I apply the voltage in reverse, I can bring the slide back. Now, right now, what I'm controlling in this device is velocity. I have here a 9-volt battery, and this is a motor that's rated to 9 volts. And so when I apply my voltage across the terminals, I get a speed that is determined from the motor velocity constant. Now, if instead of applying a direct voltage from my battery across the terminals, if I would hook up these terminals to the digital pin of my microcontroller, I could produce a pulse width modulated output to make this slider move at less than its maximum speed. I could control its velocity. However, the velocity is not necessarily what I want to be controlling. This device is a kind of prismatic joint. If I slid the slider all the way to the end, this distance here between the slider and the center of the motor where we would draw our joint, that would be A, the link length. And D, the joint variable here, is the distance that this slider has slid along its track. When I've completed my calculations from inverse kinematics to calculate the location of the end effector, what I get out is the value for these joint variables. I have a value for D telling me where I want this slider to be in order to get my end effector to its desired position. So I want to be able to control not the velocity of this slider, I want to be able to control its position. The easiest way to do that would be to use something called open loop control. In open loop control, what we'll do in order to control the position of the slider is we will position the slider at a starting point, and then we will apply a voltage to this motor for a specified amount of time in order to move the slider only a certain distance. For example, let's suppose that we did some calculations on our motorized slide potentiometer. Suppose that we did some tests on our motorized slide potentiometer and we found out that the slider moves 100 millimeters per 1/2 second when we apply a full 9-volt signal. Now, suppose that we went through our inverse kinematics and we found that D equals 20 millimeters for the desired X, Y, Z location of the end effector. How could we achieve this 20 millimeter displacement knowing the speed at the voltage of our prismatic joint? The first thing that we do to figure this out is we have to make a decision. We have to decide either one, what speed we want the slider to move at, or two, we need to set how much time or how long the movement should take. These two things are essentially the same, as you'll notice. However, in some cases, it will be easier for you to set a limit on the speed, and in other cases, it'll be easier for you to say how long you want the movement to take. So these are two equivalent ways of thinking about the speed of your motor. So let's try doing this calculation in both ways. First of all, let's suppose that we're going to set a limit on the speed of the motor. Now note that in open loop control, we're going to set a constant speed for the motor. In the future, using other kinds of control, we might vary the speed during the move. But here, for the case of open loop control, we're going to keep the speed a constant. So in this example, let's suppose that I want the motor to move no more than a velocity of 100 millimeters per second. I'm going to start by figuring out how many volts I should apply across the terminals. So I know that the speed is 100 millimeters per half second when I apply 9 volts. I want the speed to be 100 millimeters per 1 second at some X number of volts. And so I calculate that the voltage should be 4.5 volts. Now remember from the last videos that I can't necessarily produce 4.5 volts. I'm going to assume that we're controlling this actuator with a digital pin of the microcontroller. So I'm going to be producing a pulse width modulated output. I need to calculate what the duty cycle is for this pulse width modulated signal. So remember that the duty cycle is equal to the voltage we're trying to apply divided by the maximum voltage. and then times 100 because we express duty cycle in percent. So in this case, the duty cycle is 4.5 volts divided by our Vmax of 9 volts times 100%, and we get a 50% duty cycle. Now we've figured out how to move the motor at the correct speed, but we still haven't achieved our position control. In order to get to the right position, I need to set this speed for a specified length of time. So to calculate that, I'm going to scroll back up to the top to remind myself that we're trying to move a distance of 20 millimeters at a speed of 100 millimeters per second. So now I can calculate the amount of time that we need to leave this pulse width modulated signal on for. If I divide the distance by the speed, what I'm left with is time. So in order to achieve the desired position at the desired speed, I'll set a pulse width modulation output at a 50% duty cycle, and I'll leave that on for 0.2 seconds. And that should get my joint into the position of 20 millimeters at the desired speed that I've set, 100 millimeters per second. Now, this kind of control, which is called open loop control, has some pros and cons that we're going to look at in the next video.